All right, everybody. Good morning, good afternoon, good evening, depending on when you are watching this video. It is I, Dr. Kaz, and this is one of the videos that I told you that I was going to share with you. And we are going to complete the gastrointestinal digestive system. So we just finished in class the upper GI tract, as we like to call it, and now we are going to complete the lower GI tract. So we're going to start off with an overview, kind of roughly go through all the different portions of the remaining gastrointestinal tract and its accessory organs, and then we'll kind of get into it in a little bit more detail. So we just finished up with the stomach, and if you recall, I did mention that the small intestine follows the stomach, and actually considering that the duodenum is the first portion of the small intestine, that is going to actually still be considered part of the upper gastrointestinal tract, okay? But we are going to talk about it here as we're talking about the lower GI tract, right? So with the small intestine, we know, we've learned this before, that there's three portions to it: the duodenum, right, the jejunum, and then the terminal portion, the ileum. And as we know, the stomach enters into the duodenum, and I want you to think of the duodenum as the part of the lower GI tract. Well, I shouldn't say the lower GI tract because it's part of the upper GI tract, but part of the small intestine that is actually going to be a mixing area, because the duodenum is going to receive the chyme from the stomach, and the stomach has already inserted some of its digestive enzymes into that region there, and it's mixing it up like a cement mixer. So as it empties into the duodenum, now the duodenum is also going to add in its digestive juices, that from the gallbladder and also from the pancreas here, okay? So we're going to continue to mix in some things from there, okay? But the overall portion of the lower GI tract, the small intestine, this is where the majority of the chemical digestion is going to occur. In addition to that, it's also where, all right, as we've broken down whatever we've eaten and whatever we've drank, we're going to absorb most of whatever those contents were, all right, into our bloodstream and into our lymphatic system. All right, so the small intestine does play a large role in chemical digestion, okay, and it's also going to play a large role in absorption, okay? So chemical digestion and absorption are going to be in a large portion there, okay? Now, along the lower GI tract, we'll have our accessory digestive organs. That's going to include the liver, all right? We will also include the gallbladder in that, all right, and also the pancreas, okay? So keep in mind, all right, and we will discuss this in much more detail, all right? But the liver produces the bile, okay? The gallbladder stores and concentrates the bile, all right? And then the gallbladder will release that bile into the duodenum, whereas the pancreas obviously is going to produce its own digestive enzymes, and then it will secrete them from the pancreas into the duodenum also. After we move through the small intestine, we're going to arrive at the large intestine, okay? And its job is really just to kind of continue absorption, but pretty much whatever the small intestine didn't absorb, it will then absorb. A lot of it includes water, okay? And then also electrolytes, and if you're not familiar with electrolytes, it's going to be some contents like sodium, okay, potassium, magnesium, anything. I mean, technically the term for electrolyte is anything that can actually conduct electricity, all right? But the electrolytes, all right, will be absorbed from the contents there of the chyme in the large intestine. And then also our vitamins, all right? Primarily our water-soluble vitamins will be absorbed in the large intestine. And then eventually the large intestine, as we get to the distal end of it, is going to primarily compact everything down into what we call feces, all right? And then once we get to the rectum, that's really where the feces are going to be compacted, concentrated, before they're eliminated through the anus there. So you can kind of see here, all right, as we're moving through our digestive system here, okay, you can see here's the pancreas, one of our accessory organs, the liver, right? You can see a little bit of the gallbladder. They're going to release a lot of their secretions here into the duodenum, okay? And then the duodenum is going to mix it up with the chyme, where then for the remaining portion of the small intestine, we'll get a lot of absorption and chemical digestion here, and the jejunum, the second portion of the small intestine, and then the ileum, the terminal and third portion of the small intestine. And then the small intestine, the ileum, will then move into the cecum, the first part of the large intestine. All right, those chyme contents mixed in with all the digestive enzymes here, and we'll continue to try to absorb as much water, electrolytes, and vitamins, okay, as it moves through the large intestine as we start to compact it here in the rectum prior to its elimination from the body. All right, so let's get into some the details of the small intestine, okay? So pretty much, all right, the material that you have eaten, drank, when it winds up in the stomach, it can stay there for as long as 12 hours. And then once that chyme is moved into the small intestine, it can last up to about 12 hours, all right, in the small intestine, all right, before it's moved into the large intestine, which is good. Longer time, we can move it through, all right, at a significant pace where we continue the chemical digestion, because that is I want to call it a painstakingly slow process, but it is a process that takes time, okay? And so just continue to think that in the small intestine, this is where we're going to see a significant absorption and chemical digestion of nutrients and everything that I mentioned in the large intestine, all right, absorption of water, electrolytes, and vitamins. We're still going to get a significant amount of that occurring in the small intestine. But think of the large intestine as, if you watch baseball, you've got your cleanup batter who bats in the fourth position there in the lineup. That's what the large intestine basically will its function will be. It'll be the cleanup batter. It's going to come in and just pretty much try to get what the small intestine could not get, okay, before making the feces, the waste that's going to be eliminated, all right, through the lower portion of the GI tract here, okay? So like I said before, the GI tract is one big long tube, all right, except when we get to the small intestine, all right, we are going to have a significant lengthy tube here. So what we have to do is fit it all into the abdomen. So what do? We just kind of coil it back and forth, okay? And we are going to continue on here and talk about those three segments, starting here with the duodenum, okay? So as the contents, the chyme, exits from the pylorus portion of the stomach through the pyloric sphincter here, all right, it is going to enter into the duodenum here. Now, it's important that you understand that the duodenum, all right, the first segment of the small intestine, all right, is mostly retroperitoneal, which means it sits behind, all right, the peritoneum, all right, that serous membrane there. And we're going to talk about different parts of the lower GI tract, that some portions are going to be retroperitoneal, all right, and other portions are going to be what we call intraperitoneal, which means they will reside inside that serous membrane here. All right, so the initial portion of the duodenum will be retroperitoneal, while the remaining portions of the duodenum, all right, are going to be intraperitoneal. There's actually four parts. We're not going to get into that. Four parts to the duodenum, okay? So the first part of the duodenum, all right, will be intraperitoneal, and then the remaining portions of the duodenum will be retroperitoneal, okay? So it's big port. Remember, let's keep it simple, all right? The duodenum receives the chyme from the stomach, which already has been mixed up and broken down, all right, of food products and liquid with the digestive enzymes of the stomach. And then it'll continue to receive digestive enzymes from our accessory organs there, from the liver, gallbladder, and pancreas. And so we'll start to mix all of that in, all right? The next portion is the jejunum, all right? This is where we're going to see, and this is so very important, this is where we're going to see, all right, the majority of that chemical digestion, all right, and the nutrient absorption, which you're going to learn about those processes in the lecture portion, all right, how certain enzymes are going to further break down proteins, which will further break down lipids and fats, which will further break down, all right, carbohydrates, right? So we're going to see how a lot of those enzymes are going to be released and how they're going to be working on those macronutrients to try to break them down, all right, into their building blocks. For example, proteins into amino acids, all right, carbohydrates down into the simple sugars, all right, monosaccharides and whatnot, okay? So that's going to be exciting information that you get to learn about when you get into the lecture portion here, right? So the jejunum is also going to be intraperitoneal, right? So it will reside within the serous membrane. And then our last portion of the small intestine is the ileum, all right? Now, again, this makes up the majority of the small intestine. In fact, it makes up 3/5, right? But at the far end is the ileocecal valve. So now we've run into another valve. All right, we saw the pyloric sphincter, which acts as a valve in the stomach that releases contents of chyme into, all right, the duodenum. Well, the ileocecal valve, and it's aptly named because it is located in between the ileum of the small intestine and the cecum of the large intestine. So the ileocecal valve is going to control how much of the chyme that is released from the ileum into the cecum. And again, it's all on a reflexive mechanism, all right, based on what's going on in the stomach. As more contents is going to be are being moved into the stomach, and the stomach is doing its thing and breaking things down and moving it into the duodenum, well, that will signal a reflexive movement of material from the ileum into the cecum. They call it the ileocecal reflex there, okay? So you'll, again, based on reflexes, a lot of the digestive system is based on those reflexes on the baroreceptors of the walls of these organs here that stretch, and that will send information, all right, the nervous information up to the brainstem and to the digestive centers there, okay? Again, the ileum is another intraperitoneal structure, all right? And again, its job is going to be for chemical digestion and absorption. Oops, didn't mean for that to happen. Okay, so let me just get rid of that. There we go. So lining, and this is a structure that I really, really appreciate. I didn't really think about it before, but lining the small intestine, all right, are going to be these circular folds. They're also known as plicae circularis. We'll see those in a moment on one of our models here, okay? But these are these folds of the inner layer of the mucosa, all right, and also the submucosa, okay? And they act as speed bumps, because what we're going to see is, yes, they'll slow the movement of the chyme, which is good, because remember, right, it takes time to absorb these macronutrients and to break them down into their building blocks, okay? So we want to slow that down. But the big part of it is it increases the surface area. And when we increase the surface area, we're going to be able to increase more of what we're trying to absorb. Okay, and these speed bumps help to slow this down a little bit so we can get as much absorption in as we can during the time that we have the chyme in these locations here. All right, and as we move from one end of the small intestine to the other end, we'll start to see the plicae circularis, these circular folds, they'll start to decrease. Because as we change in the histology, all right, throughout these organs, we're going to start to see how, as we get closer to the large intestine, all right, parts of the small intestine are going to take on more characteristics of the large intestine. So you can see here, all right, we've got our circular folds, these bumps here. And if you can imagine the chyme just kind of rolling down, all right, through this tube here, all right, it's going to be churning and still moving, but it's going to spend a lot of time with these circular folds, these plicae circulari, okay? And they'll expose themselves as much to the surface area as possible, so we can start to break down these macronutrients, right? And we can get as much absorption as possible. And if you take note, we see, all right, the continued 4 layers here, all right? The mucosa, submucosa, muscularis, and serosa. And notice in the muscularis layer, we only have 2 muscle layers, a circular layer and a longitudinal layer. The longitudinal layer is going to be for movement, all right, from the proximal end to the distal end of the small intestine. And the circular layer will help with that peristalsis movement also. All right. So if you kind of recall back in chapter 5, when we were talking about tissues, all right, and where we find certain epithelial tissues in their location. We spent a lot of time discussing the simple columnar epithelium, all right? And that simple columnar epithelium is going to be found in abundance in the digestive tract. Pretty much we'll see it in the stomach, all right? We're going to see it throughout the small intestine, okay? Well, in our small intestine, all right, we have these small projections of the mucosa into the lumen of the small intestine. And their role, again, is to increase that surface area, because simple epithelium, never forget, simple epithelium, right? Its function is secretion, absorption, and filtration. And so when we're dealing with the digestive tract, we're going to be discussing absorption, obviously, because we're absorbing, all right, the nutrients from what we've just ingested, and secretion, because we're going to be secreting digestive enzymes. We're going to be secreting mucin, okay? And in these villi, these finger-like projections, all right, you will see an arteriole, a venule, and then in between those two structures, our capillary network. Remember, our capillary network is going to be trying to absorb those nutrients from the digestive process. And then kind of interlaced, right, within that capillary network is where we're going to see our lymphatic capillaries, right? And those lymphatic capillaries are going to be constantly absorbing any lipids, and specifically lipid-soluble vitamins, right? Lipid-soluble vitamins would be vitamin A, vitamin D, vitamin E, and vitamin K, okay? So those lipid-soluble vitamins will be absorbed into this lymphatic capillaries and then into the lymphatic system, which will eventually make its way back into our bloodstream. As you know, the lymphatic system will dump all of its contents, all right, into the superior vena cava, which will then dump it into the heart, into the heart, and it'll get pumped out to the systemic circulation. But primarily it'll get to the liver, then the liver is going to do what it needs to do with these lipids, which we'll learn later on in our metabolism chapters, chapter 2, 3, and 27. Okay, so keep that in mind. This is what we're going to see here in the mucosa. So you can see here in our small intestine, we have the villi, these finger-like projections moving into, okay, our digestive, hold on, that was a bad, let's get rid of that. 1 second here. There we go. All right, our finger-like projections, these little bumps here, which are located on the plicae circularis. So you can see, and we'll zoom in here in a moment, all right, in the intestinal villi there, you'll get to see, all right, the arteriole, the venule, the capillary bed, and the lacteals there, which are going to be, or the lymphatic capillaries, which will be located all throughout those structures there. Now, this is a little bit of a review from chapter 5, all right, when we were talking about our simple columnar epithelium. And if you recall, all right, on some of these cells, all right, when we were talking about simple columnar epithelium, you can have ciliated and non-ciliated, all right? Well, in the digestive tract, you're going to have non-ciliated, all right, simple columnar epithelium. All right, the non-ciliated simple columnar epithelium are going to have microvilli, which are these specialized extensions or modifications to the plasma membrane of the cell, okay? And again, their main function and main job is to increase, all right, the surface area for absorption. But along these microvilli, we have these specialized enzymes that are being produced. And it's these enzymes, we give them a name called the brush border enzymes, because microvilli, from a histologist's point of view, they also coined the term brush border, because when you're looking at it under a microscope, these microvilli will look like a brush border, all right, which is a fuzzy kind of structure on top of the cells. So then we named the enzymes that are found on top of these plasma membrane cells here. All right, we call those brush border enzymes. And it's these enzymes that are going to do the chemical digestion. this is where we're going to really start to see, all right, these proteins, all right, when they're broken down into smaller chains of amino acids, then eventually into the individual amino acids themselves. Or we will see some of these carbohydrates broken down into what we call polysaccharides, all right, and then eventually into the monosaccharides, all right, the simple sugars. All right, so you'll see a lot of the final touches of chemical digestion going on here, okay? So it's really, really important, okay, that we have ample amount of these enzymes being produced for proper digestion, okay? Because there's a series of all these different types of issues that folks will have that if they're lacking some of these enzymes, that they cannot actually digest and break down some of these macronutrients. And then that's where you hear folks that have some digestive orders, like someone saying, hey, I'm lactose intolerant. Well, that is because they are not producing a specific enzyme, all right, lactase, to break down, all right, a specific sugar, all right, lactose, all right, down into its simple sugars, the monosaccharides, okay? All right, so we'll see in these intestinal villi, all right, are intestinal glands. Again, their job is going to be to produce, all right, these intestinal juices, which will help to contribute to the breakdown of foods, chemical digestion there. But let's not forget, okay, we have to make sure that throughout this whole region, all right, that we're not damaging our tissues. So our goblet cells, those are our unicellular glands, are going to produce that mucin. Remember in chapter 5, we talked about the goblet cells in the non-ciliated columnar epithelium. And their job is to make the mucus, or make the mucin, all right, which will then mix with water and produce mucus, okay, which helps to protect, all right, the epithelium. And as we move from the duodenum, from the proximal portion of the small intestine to the distal portion of the small intestine, we'll actually see an increase in the number of goblet cells. And they'll constantly keep producing that mucin. And its job is to add to the lubrication of the digestive tract, so we're not damaging those tissues there, okay? Also, all right, along the small intestine, we'll have these unicellular glands, which will produce Enteropeptide Aids. What the heck is that? Well, if you haven't already learned it in lecture, Enteropeptide Aids is a zymogen, which is a specific type of enzyme that is needed to activate other enzymes, all right? So we need this enteropeptidase, which is going to then activate other digestive enzymes in the small intestine, okay? In addition to these unicellular glands, we have the enteroendocrine cells, all right, which are going to release our cholecystokinin and our secretin. If you remember, we were talking about, all right, the gastrointestinal phase there, or portion of the digestion, and we were talking about how we have the neurological control center, okay, which is going to help with controlling the digestive enzyme release in the stomach and the motility of the stomach. We have to address the endocrine portion of it, and that we mentioned CCK, cholecystokinin, and secretin, and how they act on the stomach, because they are the endocrine part, the chemical portion, which will decrease, all right, the motility of the stomach and the secretions of the stomach, okay? And then, of course, I haven't really talked about the submucosal glands, all right? But if you recall, the stomach contents, all right, are actually going to have a low pH because of the hydrochloric acid. Hydrochloric acid has a pH value of 1, which is pretty low, all right, pretty acidic. Well, acid could be damaging to tissue, all right? So we have to protect the tissues, the epithelium, right, throughout our digestive tract. And so these submucosal glands are going to produce an alkaline secretion, an alkaline mucus, which will protect the duodenum from the acidic chyme, right? This is called neutralization. How do we neutralize an acid? You add a base to it. So this alkaline mucus will act as, all right, that neutralization factor, which will help to increase the pH, get it up close to 7, which is neutral, right? Or at least take it from 1 to 4 or to 5 pH value, so we're not damaging our epithelium there. So here's a picture of our intestinal villus. Here you can see how we have, all right, you can see how we have throughout the intestinal villus, the majority of it is going to be made up of our simple columnar epithelium, which is going to have the microvilli here, all right? And then interspersed throughout the epithelium, we'll have our goblet cells, which will produce the mucin there. And then down here near the base, all right, we are going to start to see at the base here, all right, you have these small invaginations down here where we're going to have our unicellular glands, which is going to produce the Enteropeptide Aids, which is going to activate some of our digestive enzymes, which is good because an inactive digestive enzyme is useless. And then at the base here of these pits, all right, is where we're going to have the enteroendocrine cells. These are going to produce a series of hormones, all right, the CCK and the secretin here. Okay, you'll get into a little bit more detail in that into lecture. All right, so here you can see, all right, you've seen this before. All right, here's our stomach. All right, the stomach enters into our duodenum. You can see there are these little ridges here in the duodenum. That's our plicae circularis, those circular folds here. All right, and then you can see the pancreas right here in between the spleen and the duodenum. All right, and then you can see our large intestine, which is kind of surrounding parts of the small intestine. This portion over here is going to be the jejunum. And then as we get closer here to the cecum, this will be the, not the duodenum, excuse me, the ilium, okay? And then we can see the ilium here is going to empty into the cecum here. And in this area here is where our ileocecal valve will be, okay? And then you can see you have this kind of smooth like waistband elastic structure. That's called the tinea coli. That's smooth muscle, all right, which when it contracts, it makes these sac-like structures in the large intestine. Those are called haustra, all right? Some people refer to them as saculations, all right, but we're going to refer to them as haustra. Okay. All right, on further notice, you can see as we get into the large intestine, we have the cecum down here, this outpouch in here with our vermiform appendix hanging off the end. Then we have our ascending colon, which comes to a curve here. All right, that is known as the hepatic flexure. All right, also known as the right colic flexure. Then we have our transverse colon that goes from the right side of your body over to the left. Then it comes to another curvature here, and that's known as the splenic flexure or the left colic flexure. Then our large intestine descends, all right, we refer to that as the descending intestine, all right, or descending colon. And then it goes into this little kind of S configuration, and that is known as the sigmoid colon. And then the last portion here we can see is the rectum, and that's where we'll get into the storage of feces. And then finally, we have our anal sphincters. The internal anal sphincter here, all right, is going to be closer to the inside of your body. This is made up of smooth muscle. You don't really have any, obviously smooth muscle, you don't have voluntary control over it. And then you have your external anal sphincter here, all right, and the external anal sphincter is made up of skeletal muscle. This is what you have control over. This is what you learn to control or master controlling of during the quote unquote potty training portion of your life. Okay. All right. So let's kind of move away from the gastrointestinal tract per se and talk about some of the accessory glands and organs here. All right. So the largest, all right, internal organ in your body is the liver, and it does many, many different roles here. We're only going to discuss its role right now, all right, in its function of the digestive system. okay? And its main function in the digestive system is going to be for the production of bile, okay? So when you think of bile, think of fats, all right? Bile helps to break down fats, all right? Helps to what we call emulsify these fats so they're easier to digest, okay? Remember that your liver is located on the right side of your body in the right upper quadrant, just below the rib cage there, okay? So the liver, all right, like most of the organs that we've talked about in the abdomen, is going to be covered by a dense irregular connective tissue capsule. And it's also the outer portion of the liver itself will be the visceral layer of the peritoneum, that serous membrane, all right, that we've seen that lines most of the abdomen and many of the organs there, okay? So the only place that we will not see the capsule, all right, or the visceral peritoneum is going to be in what we call the bare area of the liver. And that's the area of the liver that where the liver actually articulates or is pushed up against the diaphragm, okay? It'll be on the superior portion of the liver there, on the inferior surface of the diaphragm. So our liver is made up of primarily two lobes, all right? And then one of those lobes has two smaller lobes, part of it. So essentially there's four lobes to the liver, right? We have a right and a left lobe. The right lobe is going to be larger than the left. And so we further subdivide the right lobe into the quadrate lobe with the Q and the caudate lobe, right? How I remember which is close, where one is located to the other. The inferior vena cava will be proximal, all right, to the caudate lobe. So I remember cava begins with the C, caudate begins with the C, all right? So we'll find the inferior vena cava, all right, and then the lobe, which is immediately adjacent to that, is going to be the caudate. I'll show you in a moment on a picture, okay? The quadrate lobe will be right next to the gallbladder, okay? So the right and left lobes, all right, are divided by, it's an important anatomical structure, the falciform ligament, all right? And you'll see that quite easily on the anterior surface of the liver, okay? And part of that falciform ligament is going to attach itself to the anterior surface of the abdominal wall, okay? Helps to anchor, all right, the liver in place so it's not bouncing around in there. Other structures will too, okay? This is just one of the many that help to anchor the liver there, all right? And then we'll see on the free end of that falciform ligament a structure, all right, that's called the round ligament. And at one point, it was a blood vessel, all right? It was actually part of the fetal umbilical vein. But once you are born, okay, then that fetal umbilical vein collapses and is no longer used or needed, all right? And so we rename it, all right, the round ligament of the liver, okay? So some other structures that we're going to see, all right, on the other side, or the posterior inferior portion of the liver, is going to be obviously the inferior vena cava, right? And we've also got another embryonic structure called the ligamentum venosum, excuse me, right? And again, when you were an embryo, all right, you had this structure called the ductus venosus, right? And during embryological development, all right, that structure then starts to degenerate and deteriorate, and its remnant is referred to as the ligamentum venosum. Now, the remaining structure here, the Porta Hepatis, this is basically all the entrance and exit into the liver, all right, where blood vessels and nerve structures and our lymphatic vessels are going to enter and exit into the liver, and also where our bile ducts will come out, all right, and enter into the gallbladder, okay? So that structure is called the Porta Hepatis. So you can see here on the anterior view, you've got a right and left lobe. The right is larger, all right, but these lobes are divided by the falciform ligament, all right, which helps to secure, all right, the liver to the interior abdominal wall. And then at the free edge of it down here, we've got the round ligaments of the liver, right, which is an embryological or fetal remnant structure. And then you can see the gallbladder kind of peeking out over here, right, on the inferior portion. So as we flip the liver over and we look at it from the posterior inferior view, you can see, all right, the right liver is now further subdivided into these two lobes here. Now remember what I said. The caudate lobe is going to be closest to the inferior vena cava, all right? And so you can see it's adjacent to that. And then the quadrate lobe is going to be adjacent to the gallbladder there. And then here in the center, all these blood vessels, neurological structures, which aren't pictured here, okay? And the ducts are entering and exiting out of the liver, and that's the Porta Hepatis there. And here's, again, a similar view on your model, all right, that you have in your atlas here, okay? And so keep in mind the relation, because now we've kind of, if you look at this picture here, we've flipped the liver around, all right? The right lobe is going to be on the left side of our picture. Here we can see the right lobe is on the right side of our picture here. The right lobe is the larger of the two, all right? And you have that falciform ligament that's going to divide the left and the right lobes. All right, so let's kind of delve into and discuss the histology of the liver, okay? So again, the liver has many, many functions, but we're going to focus on the digestive system functions, all right? Also, I want you to kind of think of the liver as a filter, all right? It is going to, obviously, blood is going to filter through this organ, and the liver is going to add things to the blood and take things out of the blood, okay? But keep in mind that the primary purpose of the liver and the digestive system is to make bile, all right? So when we talk about the liver, all right, we're going to subdivide it down into what we call hepatic lobules. I'll show you a picture. So the connective tissue capsule, that dense irregular connective tissue capsule on the outside of the liver, and we've seen this with other structures, that connective tissue capsule will invaginate and move into the interior of the organ itself, and it will form these partitions, these hepatic lobules, all right? And these hepatic lobules, all right, will house the functional units of the liver, all right, the cells of the liver called the hepatocytes, all right? And these hepatocytes are going to produce the bile, okay? So the liver has to export the bile out, all right? But meanwhile, as blood is flowing into the liver, it's going to filter that blood, all right? Because a lot of what was just digested, all right, in the small intestine is going to get dumped into, all right, our portal hepatic or hepatic portal system, right, which is going to be loaded with nutrients that we just digested things from, and it's going to go in the liver, and we're going to filter that out, right? So in these hepatic lobules, and you'll see these hepatic lobules at the periphery, we have these structures called portal triads, and each portal triad is going to have an artery, a hepatic artery, all right? It's also going to have a branch from the hepatic portal vein, and then also what we call the hepatic bile ductule. So these hepatocytes are busy making bile, and it's going to dump its bile into the hepatic bile ductule, which will then drain into, all right, the gallbladder. We'll get into that in a second here. Well, at the center of these hepatic lobules is a vein, and it's aptly named the central vein, okay, because it's at the center of the lobule there. And it's going to drain all the blood, all that nutrient-rich blood, okay, that has already been filtered by the hepatocytes, all right, into these structures, all right, well, not into, but it's going to receive all that blood from these structures called hepatic sinusoids. And it's these sinusoids which will drain into that central vein in the middle, all right? Then these central veins will all converge on into larger veins called the hepatic veins. Then the hepatic veins will drain into the inferior vena cava. I'll show you a picture here in a moment, okay? Now remember what I was telling you, all right? At the periphery of those lobules, we have an artery, all right? And those arteries are branches off the hepatic artery. And the hepatic artery comes off of the celiac trunk. And if you remember, the celiac trunk is that first artery, right? It's an unpaired artery, the first artery that comes off of the descending abdominal aorta. As soon as the abdominal aorta emerges from the diaphragm, it gives off the celiac trunk, which has 3 branches. Okay, so the hepatic artery carries oxygenated blood, okay, which goes to the liver and then provides oxygenated blood to all the tissues of the liver. Okay, the hepatic portal vein, meanwhile, carries, as you know, veins deoxygenated blood, but it carries that nutrient-rich blood that just came from the capillary beds throughout the GI tract. Okay, remember that's where our absorption is occurring. Okay, so the hepatic portal vein is going to travel into the liver, all right, and it's going to mix blood with all of the hepatic lobules, because you're not only getting, all right, blood from the hepatic artery, which is oxygenated blood. Okay, now we're going to mix that blood with the hepatic portal vein. Okay, all that is going to drain into those hepatic sinusoids, and then those hepatic sinusoids are going to drain into the central veins. Those central veins are going to drain into the hepatic veins, and the hepatic veins drain into the inferior vena cava. That inferior vena cava travels upwards to the heart and drains into the right atrium. A lot of stuff is going on in the liver. It's really amazing. Okay. So in our hepatic lobules here, we're going to see, all right, these hepatic sinusoids, all right, as they are draining blood from the cells that have just received oxygenated blood, all right, from the hepatic artery, and also deoxygenated blood from the hepatic portal vein, but it's nutrient rich, which is okay. So we're going to have all those nutrients that we received from the portal system, and then the oxygen that we receive from the hepatic artery are going to enter into the hepatocytes. And then those hepatocytes will drain into the hepatic sinusoids. So keep in mind, all right, that we can't leave out the immune system from this. And we have these specialized cells called Kupffer cells, also known as stellate cells, which are just basically macrophages. And those macrophages, again, will be exposed to the nutrients that were in the blood and anything, both deoxygenated and oxygenated blood. And they're going to do what they normally do, which is going to be, all right, to kind of attack and destroy any harmful substances that have entered into the liver there. Okay, so let's focus here now on bile, okay, and what its purpose is. All right, you've heard me talk about it, and you've heard me say, well, bile is primarily for, all right, the breakdown of fats, which is true. All right, do not be fooled. All right, when we use the word secreted, all right, that means that the liver is going to make the bile. The gallbladder has nothing to do with making bile. Okay, that's why if you have, all right, a cholecystectomy where they take out your gallbladder, you can still function digestively wise. All right, you have to alter your eating habits because you're no longer able to store and concentrate that bile. You're only relying on the liver itself to produce the bile and just secrete it directly into the duodenum. Okay. So there's some disadvantage to not having the gallbladder, but you can still function digestively wise. So what is bile? All right. Primarily, it's mainly made up of water. All right. But we have bicarbonate ions. Well, that's important because bicarbonate is a buffer. All right. And that's going to help neutralize, all right, or buffer, I should actually say, the low pH or the high acidity of the stomach contents. Okay. These bile salts, all right, are going to help with the breaking down, all right, of fats. All right. Also, we'll have cholesterol, and we know that cholesterol plays a large role in the production of certain hormones. It's an integral portion of the plasma membrane components, all right, on cells. And then we have lecithin and mucin. And lecithin also helps to emulsify and break down fats. And then mucin, as you know, all right, helps with mucus. Okay, so the main purpose of our bile is to mechanically digest the lipids, the fats. All right, plays a large role in that. All right, so finally, I get to show you the hepatic lobules so you know what the heck I'm talking about. All right, so as we're looking at a hepatic lobule, all right, you can see, all right, at the structure here, all right, you have, all right, here's the hepatic lobule. And at the periphery, all right, you have our triads here, okay? And these triads here at the periphery are going to be made up of, all right, a bile duct here, and then a vein and an artery. Okay, and then at the center here of our hepatic lobule, you'll see the central vein. And then you can see these spaces located traveling from the periphery more towards the central portion. These spaces, those are the hepatic sinusoids. Those will drain blood, all right, and other substances from the hepatocytes, and they'll drain into the central vein. Now let's move in a little bit closer and really kind of get an idea. So here's the central vein at the middle. On the periphery, we have our portal triad here, all right? And you have the bile ductual, all right? We've got a branch off the hepatic portal vein, and then we're going to have a branch off the hepatic artery. Now, if you notice the directional arrows here showing you the movement of substances here, pay close attention. If you notice, all right, the blood vessels are going to move their blood from the periphery towards the center. Whereas conversely, all right, the hepatocytes, they're going to produce bile, but they're going to move the bile, all right, from the hepatocytes out to the periphery. So bile moves out, blood moves in towards the center. Okay, keep that in mind. All right, because again, bile is made in the liver, we need to exit it into the gallbladder there. All right, so here are those sinusoids, they'll drain, all right, blood and other substances from the hepatocytes, and it'll drain it here into the central vein. The central veins will then converge into the hepatic veins, and then those hepatic veins are going to drain into the inferior vena cava. Okay. Here you can see a little histology slide here. Here's a liver lobule here. You can see the central vein in the middle, surrounded by hepatocytes. And then on the periphery of the lobule, you can see the portal triad there. So this picture here kind of shows you some of the blood flow here into the liver itself, all right? So you've got your hepatic portal system here, all right, made up of, here's your splenic vein, here's your inferior mesenteric vein. They both come together to form the hepatic portal vein, all right? But these veins here come from the digestive organs there, all right? Namely the intestines, and it's going to drain all those structures, and they have all this nutrient-rich material that it just got from the GI tract. And so it's going to drain all that material into the hepatic portal vein, into the livers, all right, into those hepatic lobules in which they go through the filtering process, and then from the central veins into the hepatic veins, and then eventually into the inferior vena cava. But also, let's not forget about the hepatic artery here, okay, that originated from the celiac artery off of the descending abdominal aorta. And that, again, is going to supply oxygenated blood, okay, to the liver tissues there. Okay, let's talk about the gallbladder. Real simple, real easy, all right? It is located on the inferior surface of the liver, all right? But its main function, all right? Again, I know I've said this many, many times. It does not make bile, but it will store it, concentrate it, and then release it once the cholecystokinin hormone, all right, is released, and it causes the gallbladder to contract and relax, basically pumping, all right, the bile out of the gallbladder and into the duodenum there, okay? It also will have, all right, 3 layers, okay? Now I know, and we call those tunics, as you know, all right, we're used to seeing 4, all right, throughout the GI tract, but again, this is an accessory organ here, okay? So it only has 3 layers, 3 tunics, all right? Of course, it's going to have the inner mucosa with its epithelial tissue, and then it's going to have its middle layer, the muscularis, again, a muscle layer, all right, so that when it contracts and relaxes and creates that pumping action, it will expel, all right, bile from the gallbladder. And then finally, the outer layer, the serosa there, okay? So we will see, all right, with the gallbladder, all right, the gallbladder will drain, it will receive the bile from the liver, but then it will expel the bile from the gallbladder, right? Which we call the cystic duct here. We'll see this in a second. All of this is governed by another valve here, right, which is under the control, right, of the hormone cholecystokinin. All right, so here's a nice picture. You can see, all right, the gallbladder. All right, we have our cystic duct here, all right, which is going to drain bile from the gallbladder, and it'll empty it into the common bile duct. And you can see you have two ducts here that come from each lobe of the liver. All right, so you've got your right hepatic duct and your left hepatic duct. Both of those ducts converge and form the common hepatic duct. Okay, the common hepatic duct will then merge with the cystic duct, all right, and then eventually, all right, that will form our common bile duct here, which will head into the duodenum and release, all right, bile into our small intestine there. All right, let's finally, since we're still talking about our accessory organs, let's talk about the pancreas. We learned about the pancreas before, and we talked about how it's an endocrine exocrine gland. Okay, we already talked about its function of endocrine, all right, when we discussed chapter 17 for its production and secretion of insulin and glucagon. Okay, so we're not going to talk about that. We're going to talk about its exocrine function. Okay, and its exocrine function has to do with digestion, right? The pancreatic juices that you hear about, right? First, know that the pancreas is retroperitoneal. So it's pretty far back in the abdomen there, right? Again, it's nestled in between, all right, the duodenum and the spleen, okay? So the head of the pancreas is going to be adjacent to the duodenum, okay, whereas the tail is going to be adjacent to the spleen. And as it starts to taper down, all right, from the head to the tail, all right, we refer to that region of the pancreas as the body. I think it looks like a cane to cane, whatever type of cane you think, laying on its side there, okay? So you can see the head is over here, all right, the tail is down here, and then between is going to be the body. All right, you can see how it's nestled right in here, all right, of the duodenum. Here in our model, in our atlases, you can see the same thing, okay? All right, so we've already visited and discussed the histology of the pancreas back in chapter 17, but we'll kind of refresh your memories, all right? Since we're talking about the exocrine function, all right, we'll discuss the Acinar cells, all right? These cells, again, are simple epithelium, okay? So they're either going to absorb, secrete, all right, or filter. Well, in this case, they are going to secrete something. The shape of these cells are cuboidal in nature, okay? And so they're arranged like grapes, all right, or acini, all right? So when you think of the term, when you hear the term acini, all right, we saw it before when we were talking about the respiratory physiology, all right? And we actually talked about the makeup of certain glands, all right? We heard the term first, acini, all right? So think of grape-like structures, all right, or sacs, right? And it's these sacs that are going to produce the digestive enzymes here, okay? And then when we put all of these acini together into clusters, we now refer to them as lobules here, okay? And we'll see the majority of the production of these cells are going to be digestive enzymes. But it's important to understand that we're going to be making these digestive enzymes to, again, help to break down those macro molecules there, all right? But if you recall, all right, for glands, you have the secretory portion, and then you have the conducting portion. The secretory portion is the acini, all right? The ducts are going to be those structures in which whatever was secreted those secretions are going to pass through. Well, the cells there in the ducts, all right, they have a secretory role, and they're going to secrete that alkaline bicarbonate fluid that I was telling you about. That bicarbonate fluid, all right, is going to help temper down the pH, all right, of the chyme from the stomach. I should probably say temper up, because we're going to actually increase the pH. We're going to try to make it more neutral or basic. All right, we're going to go from a very low pH and we're going to try to increase it so we're not damaging tissues. So keep that in mind. So the duct cells are going to produce the alkaline bicarbonate fluid, all right, whereas, all right, the acinar cells, the sac-like cells, the secretory cells, are going to produce those digestive enzymes there. Okay, so here's the acinine structure here. All right, that is going to produce the digestive enzymes. All right, amylase for our starches, lipase for our fats, proteases for proteins, nucleases for the nucleic acids. All right, and then our duct cells over here are going to produce the bicarbonate, all right, which is here is the molecular formula for that, HCO3, you should know that, okay? And that is going to help to buffer or to increase, all right, the pH value of the stomach chyme. All right, I'm gonna stop this video here, okay, and take a break for a moment and drink some more of my coffee, and then we'll finish up the digestive video here in a moment. Okay, so take a break, get some water, do what you'd like, and I'll see you in the next video.